I don't.
The arrow exam today, so.
I see. I see. The expo's coming up too, I'm guessing, right? So I'm sure
Yeah.
pretty much people are working on that, I'm sure too.
Posters and stuff.
Yeah. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good. All right, second to last week. Next week is our last week. Okay. All right, so we have I'm what I anticipate to be about maybe 1.5 lectures worth of content left, and so today we're going to start time marching for finite volumes. We'll probably finish it up halfway through Monday, and then that'll be it for this class. And so I think I mentioned it last week or last time we met, but my plan for next week is to basically have final project workshop. So on Monday we'll finish up the rest of this lecture. We'll probably finish about halfway through, and then for the rest of the time on Monday, or our time on Wednesday as well, for the entire lecture on Wednesday, that's time that I've dedicated to help you guys with your final projects. And so I know just because and a lot of people have been busy with other stuff, maybe you haven't had a chance to look at the code yet, and so definitely would be a good idea to look at the code before next week so that you can come to the lecture with questions and I can help you out. Okay. With that said, during finals week, of course, we don't have a final exam. We just have a final project. But I still plan on keeping my usual office hours, although they'll probably mostly be virtual, just because I live kind of far from campus right now, and it's a bit hard for me to come here. So I do plan on having regular office hours during finals week, just to provide more support for your final project. But if those times don't work for you, you can of course make an appointment to see me, and we can find a time that works for both of us. Okay. So kind of bottom line is, there's, I want to make myself as available as possible for the final project, to help you guys with the code, because, typically, it takes, especially when you're first starting out, I think when it definitely helps to get like a helping hand, with that. So, definitely reach out if you're having trouble with the final project, definitely reach out, I'll be here to help you as best I can. Okay. All right, and so with that, I think that is all my announcements. Are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and pick up where we left off. All right, so I'm going to scroll up for just a second, so you don't have to write this down because this was from the lecture last time. But where we left off on Monday was we were talking about time marching for finite volumes. So we've done time marching before, but we did time marching for finite difference method. So now we're just kind of doing the same thing for finite volumes. Okay? And so really this is kind of a merging of those two techniques. And so, just like we usually do with finite volumes, we're going to take our governing equation We're going to integrate the equation over our cell. And now that includes the time derivative term as well. The only difference now is that, for the time derivative, we're not going to apply any fancy integration rules with this. So we're not going to do any divergence theorem or any of that. We're basically just going to integrate it straight up. Okay. And then what we get from that is a time derivative term that looks the same as before. And so we're going to use basically our normal kind of explicit implicit Euler. And so whenever we see a time derivative term, we're going to plug in this expression here at the bottom. Okay. We're basically going to say partial t is equal to a forward difference in time. So phi at n+1 minus phi at n, all divided by delta t. All of these applied at the center cell, phi sub c. Okay. All right. So let's see how this works out in one dimension. Because usually we start in one dimension just because it's a little bit easier to follow. And then we'll do a two-dimensional problem. And the 2D problem will actually be very similar to the project if you're choosing to do finite volumes for the project. Okay, so let's start with 1D. And in fact, we're going to do explicit Euler in 1D. And so, of course, you can have implicit Euler with 1D problems as well. So, the only reason I'm doing explicit here is mostly just kind of for time's sake, just so that, by the time, we kind of finish in kind of a timely manner. Okay. And I wanted to say implicit for the 2D one because, the final project has you do implicit Euler with 2D. So I wanted to give you kind of more direct support for that. Okay. Okay. And so just a refresher. So when we say we're performing an explicit Euler, basically what that means is that for all the phi variables without a time index, we're going to assign it a time index of n. Remember, the time index n here is the current time step. Of course, the exception to this is time derivative terms. Remember, the time derivative has both n+1 and n, but for all the other phi terms, we're going to assign the time index of n. Okay. Okay. So let's see how this is applied in a 1D example. We're going to start with kind of our usual example. So, if you look back at all of our time marching schemes, we always started with this one just because it's relatively simple. All right, so we have partial t is equal to 3 partial squared phi partial x squared. Boundary conditions, since we are in 1D, we only have two boundary conditions here. And so what we're going to say is that phi at x is equal to 0 is equal to cosine of pi t and 2 d phi dx because of partial phi partial x at x is equal to 1 is equal to cosine of pi over 2 t. Okay. And since this is an unsteady problem, we need our initial condition. And so our initial condition is going to be 0. So we're going to assume the solution starts at 0. All right. And so for this problem, what we're going to do is we're going to use finite volumes for the spatial discretization and explicit Euler for the time marching. Okay. All right, so what we want to do is we want to, first of all, we're going to write out the 5 algebraic equations. So we're going to assume we have 5 cells first, okay? So we're going to write out what the algebraic equations look like by hand, and then we're going to implement some code. Okay? Okay. All right, let's assume a time step size is 0.001. Okay. So there's our problem. And so we're going to be, this is our first time actually doing this. So, we're gonna start with the governing equation, and then we're gonna apply basically all our techniques. And so this will be kind of a good kind of a showcase of kind of everything we've gone over in the class, or a lot of things we've gone over in the class, and seeing you, and you'll get to see us or see me kind of derive it from scratch. Okay. So before I do that, are there any questions on the problem setup here? Okay. All right. So let me write down the governing equation here again. All right, so that's the equation we're starting with. And so the first thing we're going to do is we're going to apply the finite volume method to this. So we're going to take this equation and integrate it over a cell. And so in 1D, when we integrate, we just perform just a one-dimensional integral. Okay, so we're going to integrate each term dx. Okay. Right, and we're going to do separate things on these two integrals because they are kind of different in nature. Okay. All right, so on the left-hand side, we have the integral of the time derivative. And so remember, for this term, there's nothing really for us to integrate because, we have a derivative in time and our integral here is in space, okay? And so when we integrate this, we're just going to directly apply the trapezoidal rule. Okay. And what we get from this is partial phi, partial t, evaluated at the centroid of the cell, multiplied by the length of the cell, delta x, okay? And on the right here, we're going to apply our divergence theorem. Well, calling it divergence theorem is kind of, I guess a little bit too much in 1D, but in 1D, we essentially just apply the integral. Okay? And so on the right-hand side, what we have is 3. Okay? And then if we evaluate this integral, you can see what we'll have is integral pro phi partial x. Okay. Because basically the dx is going to cancel out on top and bottom there, right? And so we're just going to evaluate partial phi partial x on the left-hand side of the cell and the right-hand side of the cell. Okay. All right, and so that looks like this. And so we're going to have partial phi partial x evaluated on the right side of the cell minus partial phi partial x evaluated on the left side of the cell. Okay. All right, so that's our first step in the finite volume method. So we haven't done any time marking yet, and so that'll come soon. But let's go ahead and put everything in terms of the cell center values. So that's going to be phi sub c, phi sub r, phi sub l. Okay. And so for now, let's just assume that we're going to have neighbors on both sides, and so we're going to develop the interior equation first, just like we usually do. Okay. Okay. And so if we assume neighbors on both sides, we're going to end up with the following. And so first we have the time derivative, and so for the time derivative, we know what to plug in for that. And so we had that up there. And so this is going to be phi sub c n plus 1 minus phi sub c at n all divided by delta t multiplied by delta x. Okay. And then on the right-hand side, we're going to put these space derivatives in terms of the neighboring cells. All right, so first we have partial phi partial x, and so on the right side. And so on the right side, that's going to be our right neighbor. Okay, so we're going to have phi sub r minus phi sub c, all divided by delta x, okay, minus partial phi partial x on the left-hand side. And so that's going to involve the left neighbors. We have phi sub c minus phi sub l, all divided by delta x, okay, just like that. Okay. All right, so in pretty good shape. So we have a pretty good algebraic expression here, but now it's time to actually apply the explicit Euler. Okay, so now that we have everything in terms of the cell center phi values, we need to assign a time index to all of these values. And so you can see here all the phi values that don't have a time index are on the right. And so those come from our diffusion term. Okay. So the phi sub r minus phi sub c, and then phi sub c minus phi sub l. So none of those have time indices. And remember, for explicit Euler, we're going to assign a time index of n. Okay. So let me just go ahead and write that directly into the equation up here. And so for this phi sub r here, we're going to assign it a time index of n. For phi sub c, we're going to assign a time index of n. Phi sub c, time index of n. Phi sub l, time index of n. So let me just go ahead and circle or kind of point to those just so you can kind of see. When we do implicit Euler, and we'll do that after this, we'll assign time indices of n plus 1. Okay, but for now we're just doing explicit. Okay. So that's about it. And so that's all the kind of, I guess, fancy stuff that we have to do, all the computational stuff. Now it's just kind of algebraic rearrangement. Okay. Don't worry about the light. It's okay. All right, so we're going to rearrange some of the terms. And so the way that we're going to rearrange this is that we're going to have all the phi n plus 1 terms on the left-hand side of the equal sign. And then all of the n terms, all of the ones at the current time step, we're going to put on the right. And one more thing I'm going to do just to make the equation, just to clean it up a little bit, we're going to divide by the coefficient on the right. And so we're also going to multiply both sides. By delta t over delta x. Okay. This is mostly just to eliminate it from the left-hand side, just to kind of clean that up. Okay. And so if we do all those things, it's all just kind of algebra from here. And so I'll let you kind of verify it. But if we do all those things, we end up with the following advancement equation. So phi sub c n plus 1 is equal to 3 delta t divided by delta x squared e sub L at n plus 1 minus 6 delta t divided by delta x squared e sub c at n plus 3 delta t divided by delta x squared e sub r at n. So this is the time advancement equation for an interior cell for this particular problem. Okay. All right. So one thing I want to note here, just before we move on, so we did kind of a half derivation here, and so we derived these equations, but we did this for a specific problem. And so one thing I want to note is that these threes here. These threes are the only reason we have the threes here is because this was the value of k for this problem. Okay. It's equal to 3. Okay. Another thing I want to note for this equation here is that we derived this equation without any convection. So there was no convection in this problem. This was just pure diffusion. Okay. And so if you did have a problem with convection, you would have to kind of go through this process again and include those convection coefficients here. And so, if you had convection, it would change this equation quite a bit. And so you'd have the u terms, but for now we just did one without. Okay. All right, any questions on how we arrived at this equation here? All right. So let's go ahead and apply this equation to this problem, and we're going to apply this to all the interior cells. And so for a grid with five cells, this is only 3 cells. So this is going to be cells 2, 3, and 4. Okay. All right, so cell 2. And so, there's a lot to plug in here. And so, we have a value of delta t we can plug in, a value of delta x we can plug in as well. Okay. And then when you do that, you get the following coefficients. So p2 n plus 1 is equal to 0.075 e1 and n plus 0.85 e2 at n plus 0.075 E3 at n. Okay. For cell 3, we're going to have all the same coefficients, but everything's moved up by 1. So that's 3 out of the 5 equations that we have so far. Okay. All right. So we're about 60% there. Okay. So now we need the equations for cells 1 and 5, the ones at the ends. But remember, these equations are going to be different because of the boundary conditions. Okay. So let's start with cell 1. Right, so for cell 1, we're going to modify the equation to account for the Dirichlet boundary condition. Okay. So let's start with the kind of the finite volume equation. Okay. And so before we plugged in for the interior cells, we had this equation here. So we have partial phi partial t evaluated at the centroid of the cell times delta x is equal to 3 partial phi partial x on the right side of the cell minus partial phi partial x on the left side. Okay. And so our Dirichlet boundary condition, if we kind of remind ourselves, is phi. So our Dirichlet boundary condition is phi at x is equal to 0 is equal to cosine phi t. Okay. And so that means that our left hand side term here, this is going to be modified for the boundary condition. All right. So let's go ahead and do that. And so on this side right here, we're going to have partial phi partial x on the left side is equal to phi sub c minus phi naught, where phi naught here is the boundary condition. So we're going to plug that right in there. Okay. And then we're going to divide by delta x over 2. Because remember, for the Dirichlet boundary condition, we only go over half a cell length. Okay, so we only go from the center of the cell to the end. All right, and so if we simplify this, and so we go ahead and plug in cosine of pi t in there, what we get is 2 over delta x multiplied by d sub c minus cosine of pi. Okay, so that's what we're going to plug in for partial phi partial x on the left side. Okay. On the right side, we still have a neighbor here, so we can use our usual equation. Right. And so if we still have a right neighbor, then this is going to be equal to phi sub r minus phi sub c, all divided by delta x. Okay. Okay, so let's go ahead and put this all together. And for the time derivative, this is going to be the same as well. So it's going to be phi sub c n plus 1 minus phi sub c and n divided by delta t. Okay. And so we put that all together, and what we get is phi sub c n plus 1 minus phi sub c at n, all divided by delta t, multiplied by delta x. This is equal to 3 multiplied by 1 over delta x, phi sub r minus phi sub c, minus 2 over delta x times phi sub c as cosine pi. All right, so let's go ahead and simplify this. And so just like we did before, we're going to solve this for phi sub c at n plus 1. Okay. And what we get is the following. And one thing I'll also do too is, since we're doing this for cell 1, phi sub c is going to be equal to phi 1. So that's our cell of focus. And then phi sub r is going to be 2, because that's the right neighbor for cell 1. Okay. All right, so we plug all this in, and we plug in all the numbers for it, of course, as well. I guess we'll do that later. We'll do that now too. Okay. And so for cell 1, what we get is phi 1 n plus 1 is equal to 0.075, phi 2 at n plus 0.775, phi 1 at n plus 0.15 cosine of pi t n. All right. Any questions on how we got that equation there? All right, so let's do this one more time, but for the Neumann boundary condition on the right. Okay. And so same thing as before, we're going to start with the form of the equation that that has these kind of base derivatives. Okay. So for cell 5, we replace partial phi partial x on the right side with the Neumann condition. Okay. And so the Neumann condition on the right, if we go back to the original problem, stated that d phi dx at x is equal to 1, this is equal to cosine of pi over 2t. Okay. So that means that in our equation for partial phi partial x on the right hand side, we're just going to plug in cosine of pi t over 2. Okay. Okay. Remember, for the Neumann condition, we directly kind of replace the entire kind of face term. All right, so let's go ahead and plug that in. And so we plug that in, we get phi sub c n plus 1 minus phi sub c at n all divided by delta t. Okay. Multiplied by delta x is equal to 3 cosine of pi over 2t minus 1 over delta x phi sub c minus phi sub l n parentheses. Right. So let's take this equation here and then we'll apply it for cell 5, right? And so for cell 5, phi sub c is equal to phi 5. And the left neighbor, phi sub l, is equal to phi 4, right? And so we plug in, we solve for phi n plus 1 just like we usually do. We end up with the following equation. So we have for cell 5, phi 5 n plus 1 is equal to 0.075 phi 4 at n plus 0.925 phi 5 at n plus 0.015 cosine of pi t over 2. Any questions on how we got this equation here?
The sub n and have on the,
Yeah.
why is that?
Oh, you mean here on this on the T?
Yeah. For cell one.
Yeah.
Cosine pi and or t sub n.
Oh, yeah. Oh, it should be T sub n.
What is the?
That represents the current time. So T is kind of like a continuous T, but the fact that we're solving this with time marching means we're marching ahead at specific steps in T. So we step ahead by delta T, then delta T, then. So it's basically the time at the current time step. Yeah. Mm-hmm. All right. So the last step that we can do is just to kind of clean these up, we can put it in matrix form, just like we usually do. Okay. So with 5 equations, it's usually not too bad to put in matrix form. Just kind of a nice way to kind of visualize the whole thing. All right. And so on the left-hand side, we have all the n+1 terms. So phi 1 through 5, n+1. This can be equal to 0.775, 0.075, 0, 0, 0. This is just the matrix form of the equation. So I'm taking all the coefficients from the previous equations and then putting them in matrix form. Okay. All right, so the first matrix that we see is everything multiplied by the phi n terms. And so those are the phi 1 through 5 times n. But because of the boundary conditions, we have some extra terms here that aren't multiplied by phi, and that goes in this kind of extra vector here. Okay. So first we have 0.15 times cosine of pi t for the first cell. Okay. For all the interior cells, we have zeros just because we don't have any source term at the end. On the last cell, we have a 0.015 times cosine of pi t over 2. Okay. All right, so that's kind of the basics of this. And so, when you're applying finite volume or unsteady problems, you're applying time marching to finite volumes. It's just kind of you apply one thing after the other. So everything that we went over just now, it's nothing nothing terribly new. It's kind of two things that we've learned before. It's just that you're applying them kind of both at the same time, right? So first you apply finite volumes to the equations. You use that to get everything in terms of the cell center values, and then you apply the time marking on top of that, either the explicit U or implicit U. Okay. All right, and so the next thing that we're going to show you is now that we have this matrix form of the equations, or at least we know how to form these matrix forms, let's see how we can implement this in math. Okay, so I'm going to go ahead and switch to my computer screen here. I actually prepped the codes today, so I wasn't distracted by basketball for the first time in a while. Okay, so this is the code that we're looking at, and so this code is posted online, and so if you go to the Canvas site, you can see here under week 15, there's a code here for 1D unsteady diffusion FVM. Okay. So that's the first example that we're doing today. All right, so let's look at section 1 of the code. So section 1, we have the length of the domain, which is 1. Big N here represents the number of cells, and so we have 5 cells. The grid spacing is just the length divided by n. Then we have the diffusion constant 3. We have the time step size. That might be a little bit different than what I have in the notes, but I think that's just to make sure that we get some interesting results. Okay. We have the locations of all the cell centers, which I don't think we'll need for this problem, but it's nice to have, and the number of time steps. Okay. And so in section 2, we're going to jump into the code. Okay. All right. And so we have we're defining the containers for our current and next solutions, right? Just like we typically do with time marching. So we have sol next and sol cur, where sol next represents the fee at n+1. Sol cur represents the fee at time step n. Okay. And then we have the file here just because we're going to write a video. Okay. All right, so let's go ahead and jump into the code here. So, with just like any time marching problem, we're going to have our time loop. And so we're going to loop from 1 to the number of time steps. Okay. And then inside each time step, okay, for each time step, we need to construct the matrices and the vectors that will advance our system forward in time. So basically, the matrix and vector that I just showed you in the notes. Okay. Okay. So first thing we have is the interior cells. Okay. So for all the interior cells, this is the equation that we're going to start with. Okay. And so so inside the time loop, you can see we have another loop, which is going to loop over space. Okay, so we have 4i is equal to 2 to n-1. And you can see here we're setting the coefficients for each of the neighbors. Okay. And so for the left neighbor, and so this is going to be on the left of the main diagonal, you can see here that we have a coefficient value of k times dt divided by dx squared. And if you apply that for this particular problem, you would get a value of 0.075 here. Okay. For phi sub c, so this is the center cell here. You can see that we have a coefficient value of 1 minus 2 times k times dt divided by dx squared. Okay, so that should be pretty consistent with your notes. So for the example in particular, we're doing this for, or what you're going to get is 0.85. Okay. And then finally, we have the right neighbor, which is a at I comma I plus 1. And that has a value same as the left neighbor as k times dt divided by dx squared. And so that has a value of 0.075. Okay. Okay. So those are all the interior cells. So next we have our boundary conditions. Okay. And so for the boundary condition on the left, we have our Dirichlet boundary condition. And so at the on the diagonal term, so this is phi sub c, we have a 1 minus 3 times k times dt divided by dx squared. Okay. We have a slightly difference here. And so you remember for the Dirichlet boundary condition, usually you basically increase this value by, or increase the magnitude by 1. So instead of -2, you have a -3. Okay. And then for the right neighbor, we still have k times dt divided by dx squared. So that's phi sub r. And then for the right-hand side vector, you can see here that we have 2 times k times dt divided by dx squared. And so if you multiply this out, so for the in-class numbers, this gives 0.15 times cosine of pi times d. Okay. Okay. And then we have the same thing for the Neumann boundary conditions. For the Neumann boundary condition, you can see here, we're defining the coefficients for phi sub L, phi sub C, and then for the right-hand side vector here, which is k times dt divided by dx times cosine of 1/2 pi t. Okay. Okay. All right. And so now that we have our matrices defined for each time step, now we can go ahead and advance forward in time. And so to solve for the solution at the next time step, we're basically going to perform the matrix multiplication that's in our notes. And so we're going to take our matrix A, multiply by our current solution, add our vector B. Okay, so that's exactly kind of the operation that we have in the notes. And then once we do that, we're going to update our current solution to this. Okay. All right, and then the rest of the code here is just plotting the solution just so you can see it, and then updating the time variable. So this is updating our value for t sub n. Okay. So in here, we're going to advance t sub n to the next time step by adding t. Okay. So don't forget this line of the code. And so I think, especially for the final project, this is a line of code that people forget just because it's kind of at the very bottom of the time loop. But, you definitely don't want to forget this. Otherwise, your code it's not going to work out. Okay, so let's go ahead and run the code. So you can kind of see how it works. And what we have here is a vibrating or a string that kind of oscillates up and down. Okay. It's going very slowly, but it's going. All right, and the reason it's kind of going up and down is due to our boundary conditions, right? So on the left-hand side, we have our Dirichlet boundary condition, and on the right, we have the norm. Okay. All right, we can watch this a bit more, but it's kind of just more of the same. Okay. All right, any questions on that code there? Okay. All right, so that's the 1D stuff, and so that is how you do explicit viewer in 1D. Right? So that was kind of a good warm up, a good appetizer. But let's go ahead and see how this is applied in 2D. Okay, so for those of you who want to do finite volumes for the final project, hopefully this is going to be really helpful because I basically fashioned the next set of notes to very closely mimic what you're going to get for the project or what you're going to do for the project, at least for the basics. Okay, so let me go ahead and stop this. Let's bring back our notes. Okay. So let's go ahead and look at implicit time marching. For 2D finite volumes. Okay. All right, so we're going to do our same procedure, and so we're going to start with our governing equation. We're going to integrate it, so we're going to apply the finite volume. Okay. Okay. So our first step is we're going to integrate our governing equation with FVM. Okay, we're going to break it down using divergence theorem for trapezoidal rule, things like that. Okay. Okay, and so after we apply those integration tricks, we can, we'll be able to apply our implicit. Okay. Okay. So that's basically just kind of a very quick one-sentence summary of what we're going to do. Okay. But of course, since we're in 2 dimensions, and since we're doing implicit, there's going to be a bit more algebra, a bit more involved in this process. But, at its core, it's basically the same thing that we just went over in 1D. Okay. All right, so let me go ahead and write out our governing equation here. And I'm going to write it in vector form just to make it a little bit easier to integrate. Okay, so our equation is going to be partial phi partial t plus we have our convection term. So that's the divergence of velocity times phi minus k times the divergence of the gradient of phi is equal to q of xy. Okay, so q of xy here is our source. We're going to do this one a little bit more generally. So, I'm doing this in terms of just generic convection velocities, diffusion coefficients, and source terms, just so that you can apply it something like the final project, for instance. Okay. So first step, let's integrate. So we're going to apply double integrals to this whole thing. Okay. So basically every term there, we're going to apply a double integral. Okay. And this is where we're going to start to apply our rules. All right. So first thing we're going to do is we're going to look at the convection and diffusion terms and then apply divergence theorem. And remember what that does is that, it basically takes this double integral, it takes an integral that takes place over the entire cell and transforms it to integrals on the edges of the cell. Right, in particular in 2D, what these are going to transform them into is basically a line integral around the perimeter of the cell. Okay. All right, so let's see what that looks like. So, and I'm going to do both those terms together just because they kind of all kind of stick together. So first we have the time derivative term. So we have double integral partial phi partial t dA, okay, plus our line integral here. And so it's a closed line integral. So that's why I kind of drew that circle there. Phi dot n hat minus k gradient of phi dot n hat yes, okay, is equal to double integral of d of q of xy dA. Okay. Okay. So next order of business is to take this line integral here. So remember, this goes around the entire perimeter of the cell, but since our cell is square, remember what we usually do is we split this up into four integrals. We have an integral on the east, an integral on the north, one on the west, and one on the south. We're going to split this into north, south, east, west integrals. All right, so if we do that, we get double integral. So the time derivative integral, we're just going to bring it down. We haven't done anything with it yet. Okay, so we have double integral partial phi partial t dA plus an integral on the east face phi dot n hat minus k gradient of phi dot n hat yes. Okay. Or I guess on the east face this would be dy. Let's be a little more specific. So same thing on the north face. Same thing on the west. And one more on the south. Okay. And all this is equal to our source term on the right. So double integral of q of xy dA. So a lot of writing in this step, but it's basically the same integral, just kind of copied and pasted 4 times. And we apply it at each of the faces. So the east, the north, the west, and the south. Okay. And remember, the main reason we break this up is that because of these normal vectors, these n hats, right? Those n hats are going to be different on each face, right? And so it kind of makes sense to split this integral into 4 so that we can apply it for 4 different normal vectors. All right, let me pause here for a second. Any questions on this so far? Okay. All right, so next step is we're going to plug in our normal vectors for each side. And so that's going to simplify these integrals pretty significantly. And then after we plug in the normal vectors, we can apply our dot product. Okay. And so that's basically going to take our velocity vector and our gradient vector and basically kind of pick out which component is on each one. Okay. All right. And so we have double integral. Partial phi partial t dA plus integral on the east face. Okay. The dot product between the velocity vector and the normal vector on the east face gives us u, okay, times phi minus k partial phi partial x y, okay, plus on the north face, we're going to have v times phi minus k partial phi partial y dx. Okay. So those are the 2 positive directions. So the east direction and the north direction are positive. So all the terms there are positive. Okay. Next, we have the 2 negative directions. So we have the west face. And so we have a minus sign integral on the west face of u phi minus k partial phi partial x dy. Okay. Minus integral on the south face v times phi minus k partial phi partial y dx. Okay. And this is all equal to q of x, y, dx, dy. So dA is the same thing as dx, dy. Okay. All right. So, I'm taking my time with this. And so, we're kind of going through each step of this kind of derivation, kind of painstaking detail, because, like I mentioned on Monday too. So when you're applying the higher order scheme in finite volumes, we're not going over that together in class. And so, if you do choose to do finite volumes for your final project, it's going to be kind of your responsibility to take the quick scheme and then apply it along with implicit Euler. And so, I want to kind of remind you of kind of all the steps that we usually take, so that when you do have to go apply the quick scheme, you kind of where to plug it in. Okay? And where you plug it in is actually at this step right here. Okay, because what we have, go ahead and circle them. We have our 4 face integrals, right? And kind of the simplest form that they can be. Right? So this is after applying divergence theorem. This is after applying the normal vectors. Okay, so we have these 4 integrals here that we can plug in. Okay, and if you go back to our lecture on Monday, remember, when we apply the quick scheme, each of these integrals kind of has 2 different forms depending on the direction of the velocity. Okay, and so this is theoretically where you would plug in the quick scheme. Okay? So for right here, so note quick scheme here. To replace our integrals or circle integrals. Of course, with the quick scheme, it's a little bit complicated because each integral there has 2 forms. And so it's actually, I think it's actually a little bit cleaner to apply the quick scheme in code first instead of by hand. But, theoretically, this is kind of where you would apply it right here. Okay, that was just kind of an aside. And so for those of you working on the finite volume final project, but let's kind of resume our usual thing. So we're not going to do quick here. We're going to use our normal scheme. Okay. So we're going to make a substitution. So for every value of phi that's circled there, we're going to replace it with a basic scheme. Okay. So for the convection terms, these are all the phi values that are multiplied by a convection velocity, right? So these are multiplied by u or v. Okay. So we're going to have phi. So we have like u times phi, but we can just say phi for now. Okay. So for everywhere that you see phi by itself, we're just going to take an average between this cell and the neighboring cell. Okay. We're going to have phi sub c plus phi sub neighbor. Okay. Divided by 2. So it's just a simple, just kind of average between the 2. And then for diffusion, for all the diffusion terms, we have partial phi, partial, either x or y. Let's do x for now. Okay. For this, we're going to use our normal kind of forward difference. So we'll have phi sub c minus phi sub neighbor divided by delta x, or the opposite. It depends on kind of which side that we're on. Okay. 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 So let's go ahead and plug all those in and see what that looks like. First, we have our time derivative term. We have partial phi partial t dA plus the east integral. Okay. All right. So for the east integral, we have u times phi. Okay. Let's scroll up so you can see it. Okay. So we have u times phi. And so let's apply our basic scheme to this. And so we have u times the average, okay, phi sub c plus phi sub e, all divided by 2, okay, minus k times our basic scheme for diffusion. So that's going to be phi sub e minus phi sub c, all divided by delta x. Okay. So let me just kind of circle this, just to kind of emphasize that this is an integral by itself. Okay, so now let's do the north integral. So we have integral on the north face, okay, b times the average. So that's our basic scheme. So phi sub c plus phi sub n divided by 2 minus k, phi sub n minus phi sub c all divided by delta y dx. Okay. This here is an integral on itself as well. Okay. And we have minus integral on the west face of u phi sub c plus phi sub w divided by 2 minus k phi sub c minus phi sub w divided by delta x dy. Okay. So here's integral number 3. And then finally, integral number 4, integral on the south face of v phi sub c plus phi sub s divided by 2 minus k phi sub c minus phi sub s divided by delta y dx. Okay. And we can't forget our source term. So integral of q okay. So a lot of algebra up to this point, but hopefully it's been not too difficult to follow. All right, so next step is to actually evaluate all these integrals here. So we have a lot of integrals that are outstanding. So let's apply trapezoidal rule to all the integrals. Just to make our lives a little bit easier too, let's assume an even grid spacing. So we'll assume delta x and delta y are the same. Okay. And then I'm just going to replace it with a single symbol delta. Okay, so every integral that we see here, we can apply trapezoidal rules here. All right, and so we start with the time derivative term. So we have partial phi, partial t, evaluate the centroid of the cell times delta squared plus. Let me go ahead and simplify this a little bit. So we have u divided by 2 times delta. So that's u delta divided by 2 times phi sub c plus phi sub e minus k. So the deltas are going to cancel out there. And so if we cancel them out, we have k times phi sub e phi sub c. Okay. Let me circle this just to kind of let you know that all this came from the east integral here. Okay. And then we're going to have similar expressions for the north, the west, and the south. So for the north, we have plus v delta divided by 2 phi sub n plus phi sub c minus k phi sub n minus phi sub c. Okay. All this came from the north integral. And we have minus v delta divided by 2 phi sub c plus phi sub w minus k and we have minus v delta divided by 2 phi sub s plus phi sub c. I put big parentheses around these just because the minus sign is going to carry through. Okay, so minus k phi sub c minus phi sub s. Okay, big parentheses. And on the right-hand side, the only thing we have left there is q times delta squared. Okay. Where that q is evaluated at the centroid of the cell. Okay. All right, a lot of algebra, but you know, we're going. You know, this is pretty painstaking detail. So normally, I like to kind of skip some steps on this, but it is kind of getting late in the semester, and for those of you who are doing finite volumes in the project, I want to make sure that you kind of know, you know how to do this, or at least you kind of see how this is done. Any questions on this so far? Okay. So the next step is we're going to apply implicit Euler. Okay. So basically for every phi term that we see here, we're going to give it a time step of n plus 1. And then what we're also going to do is we're going to replace the time derivative because we haven't done that yet. Okay. And so our time derivative term is going to be phi sub c at n plus 1 minus phi sub c at n, all divided by delta t. Okay. And then for all the other phi values, we're going to apply n plus 1 to them. So every, excuse me. So every phi term that's from the integrals there that's circled in purple, we're going to apply n plus 1 to all of this. Turn into Doc Rivers up here. Can't speak without gargling my voice. Right, and then partial t is going to be replaced by that. Okay. All right. So that's probably the most fun part of this derivation is just applying n plus 1 to all the phi terms. The fact that it's the most fun, it says a lot about the subject, I guess. Really says more about me. Okay. And so the last step here, which is the least fun, is going to be the algebraic moving around. Okay. All right, so we're going to rearrange this. Okay. And we're going to rearrange with a couple goals in mind. And so first thing we're going to do is we're going to combine all the like terms. Because we have basically 5 phi terms here. So we have the center cell as well as all its neighbors. Okay, so we're gonna kind of group everything in terms of those coefficients. Okay. And then just like we did with explicit Euler, we're going to move all the n plus 1 terms to the left-hand side of the equal sign, all the n terms to the right. The good thing is that most of the n plus 1 terms there are already on the left, so we don't have to move anything over there. It's just kind of grouping them in like terms. Okay. So this will be the last thing that I show you today. All right. And so if we do that, we get the following equation. So we get u delta t divided by 2 delta minus k delta t divided by delta squared multiplied by phi sub e n plus 1 plus V delta t divided by 2 delta minus k delta t divided by delta squared v sub n plus 1 plus minus u delta t divided by 2 delta minus k delta t divided by delta squared e sub w n plus 1 plus minus v delta t divided by 2 delta minus k delta t divided by delta squared d sub s n plus 1 plus 1 plus 4k delta t divided by delta squared b sub c at n plus 1 is equal to q at xc yc delta squared plus b sub c at n. So this right here is our implicit Euler equation for an interior cell in 2D Lyman volumes. All right. All right, any final questions on this before we wrap it up for the week? Okay, all right. So that's all I got for today. We are out of time, and so on Monday we'll pick up right here. So I have one more example to show you that basically utilizes this equation in action. The example is similar to the final project. Okay, and so you'll see how kind of the hand calculations work out for that, and I think more importantly you'll see how the code is formulated for that. Okay, and then we'll be done. And so that'd be basically everything I have for the class. And then from there, we'll just work on the final project from there. Okay. All right. So thank you guys for coming today. I know it's an especially busy time, especially for you seniors. I know you guys have the expo this Friday. And so, thank you guys for making time to come out. Best of luck with the expo. I'll try to make it out. I do have a lot of other things to do that day. I'll try. So I have a lot of advising stuff I need to do that day. So I have a lot of meetings, but I'll try to make it out when I can. So hopefully I'll see you guys on Friday. So if I don't see you guys on Friday, I'll see you next week. So I hope you guys have a good weekend, and I will see you when I see you. Of engineers, it's a brilliant name. Yeah, I'll see. I'll try to make it out on Friday. Oh, if you haven't picked up your exam, if you're here, you can come pick up the exam too. Yeah. All right, I'll say that. Alessandro came up with the name. Hey, Dominic, have a good weekend. The undergraduate, they're the senior expo, basically. So they're showing off all their senior design projects. Awesome. Yeah. Mm-hmm. All right, Abraham, any final questions before I close it up?
What exam is this?
This is for 417. Yeah, didn't you take it? We took it like last week.
Yeah. It's just because you picked it up.
Oh, he's in 417 too. Yeah. All right, thanks, Abraham. See you next week.